just want to thank the organizers. I want to thank the organizers for inviting me here. Just arrived last semester, but haven't really been able to say hi to people. So appreciate the chance to talk about what I've been thinking about. So I guess I'm probably never thinking too far from Wreath Macdonald polynomials. These are a generalization of Macdonald polynomials that in some, I guess, angle, it's a bit straightforward, but when you actually want to say what that means, it's a bit of a journey. So the first half is just like, what are these things? How do they generalize Macdonald polynomials? And okay, so I'll just go ahead. So, okay, let's just go over some maybe very bare minimum of Macdonald theory. So going to be working with lambda, the ring of symmetric polynomials and infinitely many variables. And even that might be a bit of a lie. Just these are bosons, okay. It's a great story. Why would you study this ring here? You could use the model representation theory of the symmetric groups, all of them at the same time. So you can't take on one of these alone, take them all together. Yes, one 5-year-old can beat me up, but not 1,000. And yeah, this ring structure, very straightforward ring structure here is on R given by this induction product. So if I have a representation of the two different symmetric groups or two possibly different symmetric groups, well, those two symmetric groups sit inside a larger symmetric group. Here's the order is the sum of the orders, and you can just induce up. So, okay, maybe in terms of representation, it's not so straightforward what this induction product looks like, but then there's a conjugacy classes, or for example, if you have like a cycle in sigma n and a cycle in sigma m, you just put them together. You get a cycle type in sigma m plus n. So this is modeling. And just going through the story for a partition of n, lambda partition of n, you have an irreducible representation. I'm going to index it by v lambda. And this Frobenius characteristic that I failed to say verbally above here, this isomorphism, sends v lambda to some function called the Schur function. And so I'm just going to abuse notation and just drop this Frobenius characteristic notation, and I'm just going to pretend R and lambda are this thing. And if this bothers anybody, I'm going to be doing this very, very, very much. So just bring that up. Okay, so the Macdonald polynomials, P lambda, they have two well-known characterizations. First one is, you defined a doubly deformed, so QT deformed pairing on lambda or representation symmetric groups. It deforms the character pairing on the representations. I guess you call this the Macdonald pairing, and P lambda is obtained by performing Gram-Schmidt on S lambda with respect to dominance order on lambda. Now, this is not quite a definition because to Gram-Schmidt, you need a total ordering of the bases you started with, and dominance order is not total. So it's not obvious that if I pick two totalizations of that order, you'll get still the same basis. So usually at the same time, then what saves the day? Turns out that the P lambdas provide a normalized, or they provide a eigenbasis of the Macdonald operators. And so you just got to specify how you want to normalize them. So the first characterization just kind of follows a pretty established pattern in defining new distinguished symmetric functions. You just deform the character pairing. You do it once. In some ways, you'll get, how little would you turned out so well. Why don't you do it again? And the second characterization is tied to integral systems. So these Macdonald operators are related to the quantum Hamiltonians of the trigonometric Reissner-Schneider system. And in that world, you'd love to have an eigenbasis for Hamiltonians. So in summary, this is like sine and cosine, right? They're orthogonality over some pairing, and then they normalize some operators, or diagonalize some operators. Okay, here's a definition that might be strange. Well, it might be strange, not so obvious like what it's good for. So for each sigma n, I'm gonna define, or just point out you have this reflection representation, Cn. And so for partition lambda of n, this transformed Macdonald polynomial is characterized by three conditions. First is when I tensor with this, kind of total exterior, well, Q-deformed exterior, I don't know, powers of this reflection representation, that it lies in the span of these irreps. So the irreps that show up are, or equal to lambda. So it's kind of like a triangularity condition, but after applying this operator. With the Q's. The second one involves the T's, well, T inverse really. You want this to lie in the opposite span of irreducibles. Okay, so after performing this tensor product, I am a virtual sum of these irreducibles here. So an opposite triangularity, and then you've got to normalize. You just want to normalize this so that the trivial representation for sigma n shows up, just with coefficient 1. So,
just very quick question. Maybe you said this, but what's the kind of representation theoretic interpretation of the original Macdonald polynomial P lambda? Say, how is it? What connection does it have with the symmetric group representation for lambda?
Yeah, I'll get to that.
Oh,
so
okay.
that's a well. That took a long time to answer.
Okay.
So we had these P lambdas. I have this H lambda. I used a different letter because they're different. And so P lambda, right? You had this P lambda was kind of triangular. So P lambda, you can write it in terms of the Schur functions that are less than or equal to it, to lambda. There's the Schur functions for mu with mu less than or equal to lambda. So you kind of have this triangularity. Don't know what this really corresponds to for P lambda, but it turns out that P lambda is just this this tensor product in H lambda properly renormalized. Right, these are normalized so that somehow this ends up, the coefficient of trivial representation is 1. P lambda, you wanted to normalize it so that S lambda shows up with coefficient 1.
Can I ask a quick question as well? So is this like characterization 1 through 3, like is this kind of like an effective way of actually figuring out like formulas for the H lambdas? Like you can sort of like build it up? No, not enough?
No. Well, you're asking the wrong person. I think like every time I tried computing these with this definition, it just felt like a miracle, but I'm bad at computing things. So the answer could be yes, but my personal answer is no. Very bad. it just feels like an accident that he can do it.
Let me ask another maybe naive question. Does H lambda associated two bases?
Yes, they are. Wait, sorry, H lambda and P lambda. They are two different. Yeah, they're both bases.
I see. And, I mean, because we say that it's Macdonald polynomial. I mean, for example, like Cauchy-Darmstadt polynomial. I mean, they associated two different bases of the I mean, Hecke algebra. And do we still have such theory for the Macdonald polynomial?
I mean, to some degree, like, well, I'm not quite sure how to answer that question. Like do these kind of, right, like, I guess there's multiple ways to answer that question, right? So one, right, the Cauchy-Darmstadt, well, so, yeah, I guess one thing is just, so these are kind of like Cauchy-Darmstadt polynomials that like, right, Cauchy-Darmstadt, you have a triangularity condition, right? And then like a bar invariance.
Yes.
And that's kind of like secretly two triangularity conditions, right?
I see.
Yeah, and so this one, okay, yeah, there's something nice about the definition that it is a double triangularity definition. Somehow these two triangles like intersect at a one-dimensional subspace, and you gotta specify the coefficient.
I see.
So, but as far as further analogies, I'll have to think a bit more.
Can you say something about how to relate this characterization with the other ones? I mean, so if you start with the other definition, that is more workable, how would you prove that these things are true and vice versa?
Yeah, yeah, I could say that. I will probably need to, I didn't mention very much about the pairing. So let me, oh, can I new share? I can't new share. Let me stop share. And then, oh. Okay, crap, sorry. There we go. Okay. Hey, you. I figured that was you. Okay, so the main deal is just that like the so you have this Macdonald pairing. I'm just gonna write a QT. And I'm gonna write this these tensor operations as lambda Q and lambda T, I guess inverse. And I guess the point is, so first off, not made, well, if you know what the Cauchy resolution is, then you might eyeball that, okay, these are actually invertible operators. And this Macdonald pairing is a pairing, lambda Q, lambda T inverse. Now, these operations are, right, these tensor operations are self-adjoint. So, okay, so let me just say one thing. So, right, so you have that the P lambda and the P lambdas and mu's, the P lambdas are an orthogonal basis for the Macdonald pairing. Then the H lambdas are actually an orthogonal basis for this kind of twist of the character pairing. So what did I say here? I said P lambda is lambda T, a little inverse here applied to H lambda, right? So like, okay, so basically, sorry. So what I'm trying to set up here is that, right, this double triangularity condition for H lambda precisely makes it so that like, right, I apply it to here, precisely makes it so like the, if lambda is not equal to mu, right? Yeah, so sorry, I'm fumbling here. So if lambda is not equal to mu, let's say if lambda is greater than mu, if I apply lambda q to, okay, sorry. If lambda is greater than mu, if I apply lambda q to H lambda, and then lambda T inverse to H mu, right? The Schur functions just don't show up, right? The Schur functions for one don't show up and for the other. Right, this one, everything's greater than lambda. This one's everything's less than mu. And they will, if I flip the relationship, well, since these are self-adjoint, you could just kind of move them around. So that's how this double triangularity and intersecting in only one dimension is tied to the orthogonality for P lambda and P mu with respect to this slightly altered pairing. I don't know if I was successful.
No, thank you. No.
Okay.
I mean, the main point seems to be that the pairing is expressed in terms of these two operators. I mean, from the after that, it's
yeah, right on. Yeah, it's those two operators, and then because of this double triangularity, it forces actually the orthogonality.
Okay.
And you can live wild because everything's self-adjoint and commutes, so you can just move all these things around. Okay. What? Okay, it seems like. Okay, I don't know what's going on here. Okay. Anyways. So, okay, maybe there is a sense of how this is a good definition, but trying to get to Peter's question. So, yeah, what does it mean in terms of representations? So let's look at this Hilbert scheme of endpoints on the plane. This parameterizes ideals and polynomial in two variables whose quotient is n-dimensional. There's a natural torus action on the plane, which then acts on ideals. So, and the fixed points correspond to monomial ideals, which you can also index by partitions of n. And then just the, it's geometry and representation theory. So also point out that Hilbert is also distinguished in being a symplectic resolution of this symplectic singularity here. So yeah, people asked Peter's question. Well, I guess Macdonald did, and it conjectured. So when you expand the H lambdas and the Schur functions, that the coefficients lie in NQT. So right, basically H lambda is an actual, not virtual, but actual bigraded representation. And it's very strong because a priori this is even like CQT or maybe QQT or C rational functions in QT. This is called the Macdonald positivity conjecture. This was proved by Heyman. You asked if it was an actual representation. Here's what it is. Here's the representation. So he constructed this T cross sigma n equivariant vector bundle on Hilbert of C2. This is called the Procesi bundle, whose fiber at the fixed point corresponding to lambda is exactly H lambda. And well, okay, I guess you can, also bootstrapping from the Bridgen-King-Reid result. One other thing that distinguishes this bundle is that it induces a derived equivalence between the equivariant derived category of the Hilbert scheme And right, this is the equivariant derived category for that singularity that it resolves.
My understanding is that this result strengthens the result of Bridgeland, King, and Reid, right?
Yes, in the sense that he like actually gives a description of the Purchase, but well, yeah, actually, yeah. Honestly, I don't understand. I don't remember enough about the BKR to quite answer that question off the top of my head. But it gives like a explicit construction, but it's kind of like what you would do in the BKR. Yeah, sorry. Or maybe for BKR, this is just like a Fourier-McKay transform. Maybe not so straightforward. That's the same as tensoring with this vector bundle. Yeah, that might be the strengthening. Yeah, somehow this PN is like the push forward of the structure sheaf of that correspondence. Not obvious it's a vector bundle. And so yes.
So let's see. So you said that this vector bundle is T cross SN equivariant.
Yes.
I'm confused because I don't know what the SN action is.
Yeah, and a part of that is, yeah, I guess, yeah, so I haven't really said how this has gotten. Yeah, I could write something down. Sure. Sure. Yeah, so I guess so. You have this singularity. You have Hilbert resolving it. You also just have the quotient map. And then, so I think the BKR result is that, so you could take this reduced pullback here, fiber product. This is called isospectral Hilbert scheme. I'm going to call this, well, there's no other pi, so I might as well call it here. Call it pi here, so sorry. And then Pn is the push forward of O pi n. So I think BKR is just saying like this thing here, the Fourier-McKay transform. They'll yield that derived equivalence. Heyman probably strengthened this to say this is exactly, this push forward is a vector bundle. And yeah, sigma and x here.
Thanks. That makes sense.
Okay. Yeah, so the two tensor products, the definition of H lambda, you could kind of view they're kind of like pullbacks of the Cauchy resolutions, the two halves of Cn there. I guess if I have my torus act, by Q and then T here. Okay, so the Wreath Macdonald polynomials really generalizes this Macdonald positivity story. So let's track through what this means. So first off, we generalize it, or it's generalized to this Wreath product with cyclic group. I'm gonna call it gamma n. Well, okay, it also has a reflection representation, and it's no longer self-dual. So if I want a symplectic singularity, if I want gamma n to act, symplectically on two copies of the reflection representation, it needs to be one copy with the dual plus the dual. And Heyman's idea is just, okay, well, you have the symplectic singularity. Let's just look at its symplectic resolution. Now, unlike before, where Hilbert was basically like the unique one of the isomorphism, now we have like infinitely many possible non-isomorphic resolutions, and they're all Nakajima quiver varieties for the cyclic AL affine AL -1 quiver. So L nodes, one-dimensional framing. And somehow, N is tied into the dimension vectors here. To just tell you which of these Nakajima quiver varieties resolves that singularity. Yeah, so I'll need some notation. So for a box, a partition, the content is GI. This is basically the diagonal where that box is. And once you fixed an L, you can have this L content vector for a partition that just counts the number of boxes with content concurrent to I mod L, so each class mod L. And so Gordon showed that that these cyclic Nakajima quiver varieties resolves these singularities precisely when V, you could write V as, okay, so N times the diagonal vector plus the L content vector of what's called an L-core partition. I think I get to that later. And moreover, when this is the case, okay, I guess there is a two-dimensional torus action and its fixed points are indexed by L tuples of partitions such that the sum of their parts are all N. The sum of their parts is N. I'll go through what L-core is here. So yeah, I guess, oh, actually, never mind. Yeah, sorry. So what is an L-core? It's basically a way to break up a partition. So I could, to each partition, I could assign an L-core partition. I'll say what that is, and then an L-tuple partition. So this is actually a bijection here. This is called the Core-quotient decomposition. And roughly speaking, what you do is, well, in the L-tuple, this L-quotient, you are recording ribbons of length L that you can peel off your partition here. And the L-core is what's left over. So what is an L-core partition? It's one where you can't peel off anymore. Partitions of length L. So here L equals 3. I could peel off this guy, I could peel off this guy, and then there's nothing left here. And the core is what's left over, 3, 1. And then for the quotient, yeah, I mean, I'm not going to explain exactly the rule, but you have it's an L tuple, and you record, okay, first you make an arbitrary choice of where I say a strip starts. I'm going to say it's northwest, the northwesternmost box, and then you just record the class mod L of its content. So these both have content. So this strip has content 0. Okay, this is a -1 or 2, right? Congruent to 2 mod L, 2 mod 3. And it's like, similarly, this is also congruent to 2 mod 3. And so both of the boxes corresponding to these ribbons go to the coordinate you assign to 2. And then, yeah, basically because like the endpoint of one is horizontally adjacent to the starting point of the other, you're actually going to make them horizontally adjacent. Okay, so thus we have a bijection between partitions, and okay, well, let's translate this L-core and L-quotient decomposition in terms of those resolutions, right? The L-core is indexing the resolution you picked, and then the quotient is indexed fixed point on it, that resolution. So if you really want to repeat this Macdonald positivity story, your new Macdonald polynomials really should be indexed by partitions again.
Sorry, can I ask?
Yes.
So the L, you had the L content, I think. Are you saying
L content vector?
The L content vector can be read off of the core? Is that what you said, or is it determined by?
No. So sorry. Yeah. Let's go. So to answer that question directly, no. It's just that. So yeah, which dimension vectors resolves this one for gamma n? It's the ones where you subtract off n times the diagonal, and you're left with the L content vector of an L core. So, I mean, the main idea I just want to get by is just that it's the cores index the resolutions, right? So for each n, all the resolutions are indexed by L cores. And this is how the L core shows up, manifests itself. Its L content vector shows up at the.
I see. I imagine the core being kind of a fixed thing. So that you said the core determines which Hilbert scheme we're looking at?
Exactly, yeah, which resolution. Which geometry.
I see. And then the rest of it indexes the fixed points on that.
Yeah, the L quotient, exactly, right on.
Okay. Okay.
Oh, I have a question.
Yes.
I remember for Hyman's proof for the positivity conjecture, I think one of the key factors that for the isotropical Hilbert scheme, it has Gorenstein and rational similarity. And does this also hold for the the quotient and the action case? And for the
it is not known. Yeah.
not known.
Yeah, and pretty much not explored.
I see.
Yeah, I think I'll get to yeah. So the proof for this analog is completely different. Okay. Yeah. So the new Macdonald polynomials, they should be indexed by partitions again, and this might be surprising if you know anything about representations of Wreath products, because well, for Wreath products you also have a Wreath Frobenius characteristic, but now yeah, it's with L tensor power of lambda. Right, so these have a base. Each lambda, right, has a basis that's like, you know, indexed by partitions. So really, this has size like L tuples of partitions, right? Like this has a basis indexed by L tuples of partitions. I'm going through it now. Yes, the reducibles of rep gamma n are indexed by an L tuple of partition with size n. And so you have a basis where, right, you could just take S mu of I, that's just the Schur function plugged into the ith tensor and ones everywhere else. You can take the product, you know, according to the L tuple. And the Wreath Frobenius characteristic sends this irreducible to this kind of multi-Schur function. So it's always like, it's a little surprising that these Wreath guys, the Wreath Macdonald guys should be indexed by them, ordinary partitions again. On the other, yeah, okay. So anyways, so Heyman wrote down this definition. Okay, so for lambda with its quotient, you know, having parts summing up to n, this Wreath Macdonald polynomial, I'm still going to call H lambda, is characterized by, yeah, a similar tensor product here. But now you want it, right? You want crap. Okay, so let me just span. So you want it to line the span of these v mu's, where mu is greater than or equal to lambda. Now let me say what I mean by this. I want v mu to be equal to v of quotient of mu. Sorry, yeah, there's a little typo. There should be quotient of mu. Right, I have irreducibles indexed by tuples of partitions. So if I have a single partition, that doesn't make any sense. yeah, this should really be V sub quotient of mu. So I want to lie in this span of the irreducibles, but I'm going to specify that the cores are the same. Oh yeah, this is full of typos. My bad. So yeah, again, the opposite tensor product here, you want it to be kind of in the opposite span. This should be core lambda equals core mu. Sorry. And this should also be V sub quotient of mu. And the trivial representation should have coefficient 1. So one way to view this is like, right, so there's an analog of that Macdonald, the definition of the transformed Macdonald polynomials. Now, when I specify a core, I get a new ordering on L tuples of partitions. Right, you just take that core plus your L tuple, you get a partition, then use dominance ordering there. And just kind of saying like, you're just modeling that definition, but now each time you got to specify a core, and that gives you a new ordering on the irreps. So not obvious that these things that exist. Their existence was proved by Bezer-Kovnikov and Finkelberg, and by constructing an analog of the Procesi bundle. And yeah, it kind of does what you would then expect. So, right, to a geometry, so an L core and a fixed point, so an L quotient, you get that partition lambda, and the fiber of the Procesi bundle on that geometry is H lambda. And this is a bit historical revisionism. I mean, so how did they find this bundle? Well, this was first work by Bezer-Kovnikov and Caledon, constructing bundles that realize, a similar derived equivalence for these symplectic singularities. And so answering Yu's question earlier, like these things in that Bezer-Kovnikov Caledon work, they're like constructed like mod P. And then for big enough, all sufficiently large P, and then you glue them together somehow in mod or in characteristic 0.
So they're using some kind of reduction to characteristic P scale, right?
Exactly, yes.
I see.
So very much not like isospectral Hilbert scheme, right? So that aspect of the story is just like, who knows? In exchange, these bundles are very non-explicit. And yeah, so this is kind of the rest of the theory behind these Wreath Macdonald polynomials was not really developed. So diagonalization of some operators, pairing, not even more like saying like all the combinatorics in Macdonald theory as well, totally unexplored. So kind of my thesis work was trying to just looking at this picture and kind of realizing you could do a few things. So first off, I'm going to decategorify these derived equivalences using a localized equivariant K theory. And this is just representation ring. And then, turns out you can index L cores using the AL -1 root lattice Q. So right, if I add up over all the resolutions, right, to each copy of the singularity, I'm going to have like infinitely many resolutions indexed by L cores. So these derived equivalences yield an isomorphism vector spaces where when I add over all the resolutions, okay, well, they map to, each of them maps to here, but then you have, C of Q many resolutions to each copy of the symmetric function, or yeah, sorry. And by definition, this this, I'm gonna close Discord. These derived equivalences map the structure sheaves at fixed points to the Wreath Macdonald polynomial, but I'm going to add an index for the core here. Yeah, so, the observation. Oh, sorry.
Sorry. Yeah, can I ask? So are you thinking of now? Okay, so your Wreath Macdonald polynomials are now indexed by L tuples of partitions.
Exactly. Yeah. Right.
You sum over cores.
Yeah. Yeah. Right on.
Okay. This might be a silly question. Is that a finite sum? Are there?
Here?
Oh, sorry. Yeah, that's a series, right, or whatever in Q.
Sorry.
Like each L tuple corresponds to you have infinitely many possible cores, right, or no?
Yeah. But when I write H lambda, right, I'm specifying a partition, just a single partition, so I'm picking out a core.
Okay. So you continue to index them by lambdas and not tuples, L tuples.
Yeah, right on.
Okay. Thanks. Sorry.
That's fine. Yeah. So this kind of you have this kind of bosonic space here. I'm going to call it W, and you have this geometric space here. I'm going to call K. And the observation is that both carry an action of quantum Toroidal algebra of rank L. So, yeah. And how can you just use that to do things? So let's get to know this quantum Toroidal algebra. So before doing that, let's just go over quantum affine. And it has two presentations. You have your usual Drinfeld-Jimbo presentation, where you have kind of Chevalier generators, but indexed by the AL-1 affine AL-1 root lattice or root system diagram. On the other hand, you have the new Drinfeld presentation in terms of currents. So you take your generators, you put them in a generating series. But now you have a AL-1's worth of currents, right? These go from 1 to L-1. So finite eigenworth of currents. So roughly speaking, kind of cartoon pictures, a quantum Toroidal algebra, you have an affine's worth of currents. So currents, but now indexed from 0 to L-1, plus some additional kind of generators, like central generators and stuff. And a key thing I want to highlight on is that these kind of Cartan currents, okay, if I just take out the this kind of Cartan part, these generate a rank L Heisenberg algebra. So the action on the K theory of those cyclic quiver varieties, that was discovered by Varignolo and Vasero, following standard kind of scheme of Nakajima. Furthermore, Nagao showed that this is isomorphic to, it's called the Q-deformed semi-infinite wedge representation of Kashiwara and Mio-Stern. So this K-theoretic representation is like secretly kind of fermionic. And under Nagao's isomorphism, the fixed point class in K-theory is what's called the spin-on basis element. So yeah, why is it? And this is kind of non-trivial work. So it's not straightforward in the K-theory story that like it's kind of fermionic in nature. It's written down in terms of a basis that is that on which this Heisenberg subalgebra acts diagonally on. Okay, so it's kind of like a Gelfand-Seidlin basis. Now, on the other hand, on the bosonic side, in terms of on the symmetric function side, you have just the good old vertex representation. I guess defined by Yoshihisa Saito, but there's a long history of doing these kinds of constructions, I guess due to Frankel and Katz. And here the Heisenberg acts by just multiplication by bosons. So on the other hand, on the one hand, while on K, H acts diagonally, on W, this action, I guess, well, if it was finite dimensional, it'd be no potent. Right. It's like off diagonally. So there's no chance that these two representations are isomorphic, but the discrepancy is like the one between just multiplying by symmetric functions and then acting by Macdonald operators. So you're kind of off by something like a Daha Fourier transform. And this is provided by this Miki automorphism. So, so this Toroidal algebra contains two copies of on affine algebra. One, you just take the zero modes of your generating currents, so constant terms. And it's manifestly Drinfeld-Jimbo. And on the other hand, you could just take like the currents from 1 to L-1 rather than starting from 0 to L-1. And that's manifestly presented in the new Drinfeld presentation. So usually call the first one horizontal and then the second one vertical. I guess similarly, you just call usually the vertical Heisenberg. Oh, actually, sorry. Before I even say that. So there exists, so Miki showed that there's this automorphism of EQSL of the Toroidal algebra that interchanges vertical and horizontal copies of the quantum affine.
So I remember for the GL1 case, I mean, there are also, I mean, two horizontal Heisenberg algebra, and I remember the vertical part is just generated by the Macdonald operator, right?
Yeah, when you act on like, I don't know, like Hilbert schemes, yeah.
I see.
Yeah, so which is analogous now, right? I said in that K-theoretic action, the vertical Heisenberg, or just H, acts diagonally on that basis, right? The fixed point basis. So, yeah. So yeah, I'll call H the vertical Heisenberg, and then this is really var pi is the H, the horizontal Heisenberg. And so Sasha Tsimbaliuk showed that the vacuum map. So I guess this is the vacuum in W. I just go to the vacuum in K. Showed that this induces a pi-twisted isomorphism of modules. So these are isomorphic up to a Daha Fourier transform type of thing. And so, so H is diagonalized on K, and you might ask, well, what's the diagonal? What diagonalizes the horizontal Heisenberg in W? And this is just only, this is like a vacuum to vacuum map. The rest of it is just like, you just let symmetry thing unexplicit. So the first result of my life is that Tsimbaliuk's isomorphism basically sends the Wreath Macdonald polynomial. So that's something in W to this fixed point basis element here, or spin on basis element. So in particular, these diagonalize the horizontal Heisenberg subalgebra. So they analyze some operators, what are the Wreath Macdonald operators? So for the rest of the talk, I did promise talking about norm formulas, but I didn't think I could fit everything in a 1 hour talk. So for the rest of the talk, I want to talk about maybe trying to define something like this. Okay. Right. So, and I want to point out this whole entire time I've been treating H lambda in terms of, just L, in terms of bosons, how are these as like just regular functions? Okay. So trying to connect to integrable systems. Well, one way to connect Macdonald polynomials and the Reusner-Schneider integrable system is via this the spherical Daha. You have X generators. So the usual Daha has X generators and Y generators, and then these Hecke algebra generators. And the spherical Daha is it's a symmetrization of these guys. Symmetrize away the these Hecke generators. And Daha has this function, this polynomial representation where the xi's just act as multiplication and the y act by difference operators. And when you symmetrize, you'll act on symmetric polynomials. And basically, you could realize the Macdonald operators as certain symmetrized expressions of the y's. Now, yeah, I want to emphasize that, like, basically all I know about Wreath Macdonald, the Wreath Macdonald polynomials comes from leveraging the quantum toroidal algebra. So if I want to study maybe what's an analog of the Daha for the Wreath guys, I should at least study the spherical Daha in terms of the quantum toroidal algebra for GL1. Okay, and you can do this thanks to Schiffman and Vassereau. You have this surjection from the rank 1 quantum toroidal algebra onto this spherical Daha. And yeah, up to possibly doing the Miki automorphism, this sends the horizontal Heisenberg to the pure X expressions and the vertical Heisenberg to the pure Y expressions. So like what you just said, sending it to Macdonald operators. The vertical Heisenberg goes to the Macdonald operators. And moreover, this kernel, it's even like explicitly described, for example, by Philippe and Renaud. So trying to have spherical Wreath Daha, I just expect you should have something like a quotient of this higher rank toroidal algebra. Okay, but I was talking about integrable systems. What's going on? Why am I talking about spherical Daha? Well, so this quantized, I guess, really a completion of the phase space of the Reisner-Schneider, the trigonometric Reisner-Schneider integrable system. So Chalak and Farone have described this the phase space of the trigonometric spin Reisner-Schneider system with L internal degrees of freedom as a multiplicative quiver variety for this Jordan quiver. So L is in the framing. And when L equals 1, you get back to here. And yeah, you can quantize these multiplicative quiver varieties. So in David Jordan's thesis, that's basically that topic. And even in the case of L minus, so I guess in the case for like general L, this is kind of the only way I know how to quantize these multiplicative quiver varieties. And in the case of L equals 1, it's not even known if Jordan's quantization is isomorphic to the spherical Daha. So the spherical Daha like quantizes that that quiver variety, but it's like we don't know if Jordan's quantization is isomorphic to spherical Daha. So you could possibly have multiple non-isomorphic quantizations. And so this isomorphism is known in the case just n equals 2 and generic Q, or Q, yeah, you're basically like formal neighborhood of 1 and Q a root of unity. So for general N and generic Q, not known. And maybe going over some of like the argument. So this one is like just generators relations. On both sides, find generators relations, show they're isomorphic. This is just general formal deformation arguments, which so it's not necessarily explicit. And then this uses geometry. So trying to get the quantum toroidal algebra in this story here. Well, so in the case even L equals 1, this multiplicative quiver variety is isomorphic to the GLN character variety for punctured torus with the certain conjugacy class assigned to the puncture. The monodromy you're saying you want the monodrome around that puncture to be in this conjugacy class. And the ring of functions on this character variety is generated by, well, traces of monodromies along closed curves. Oh, yeah, closed curves in torus. And in this case, Jordan's quantization coincides with the quantized character variety defined by Alexeyev, Grossa, and Shomeros. It's like in the 90s. And in their quantization, there's kind of natural elements quantizing these traces over kind of the AB torus knots. These are like quantum Wilson loops. And yeah, very tantalizing. It'll be very tantalizing. So this toroidal algebra for GL1 is generated by slope subalgebras. Yeah, these subalgebras, they're indexed by rational numbers A over B. And yeah, just trying to get a certain direction. Hopefully the quotient is exactly the spherical Daha, two Jordan quantization. And yeah, it's kind of what you like to do is you want the slope subalgebra A over B for A over B to be mapped to the subalgebra generated by Wilson loops on the AB torus knot. It'd be a very pretty picture. And hopefully along this whole way, figure out clues for how to do this for general L. And then if you could figure out that quotient, then maybe you have this Wreath spherical Daha that would quantize the spin Reisner-Schneider integrable system, the phase space of the spin Reisner-Schneider integrable system with L degrees of freedom. Yeah, that's all I have. Sorry, yeah. Yeah, and